Okay, let's dive into this, because we are looking at a genuine scientific mystery here. Tucked away in these super precise nuclear physics experiments, there's this persistent, nagging signal. A signal that could point to a brand new particle, one that might completely rewrite our understanding of the universe. Or, and this is the big question, it could be nothing at all.
And that's really the heart of it, isn't it? Is this strange little blip in the data the very first hint of a fifth fundamental force of nature, something beyond the four we know and love that govern everything from gravity to your phone screen? The stakes, it couldn't possibly be higher.
So, where did this all begin? Our story starts not with some giant, flashy collider, but with a strange anomaly, a persistent, unexpected signal spotted by a team of researchers in a lab in Hungary. It was the first clue that something might be lurking just beyond our current map of physics.
And when you look at the timeline, this is where the plot really starts to thicken. It all kicked off with this one strange observation in beryllium way back in 2015. But then, the same team found similar oddities in other elements, like helium and carbon. Okay, so a pattern seems to be emerging, right? Well, just as things were getting interesting, a totally different experiment in 2023 failed to see that original signal. And this conflict is exactly what prompted a major rethink, a new paper trying to make sense of all these confusing puzzle pieces.
Now, to really get what they were looking for, we need a super quick physics primer. Don't worry, it's not too complicated. They were studying something called a nuclear transition. Just imagine an atomic nucleus that's all hyped up with extra energy. To calm down, it has to get rid of that energy, either as a flash of light, what we call a gamma ray, or by creating a pair of particles, an electron and its antimatter twin, a positron.
And here's a look at their setup. The scientists at Atom Key were basically just watching these electron-positron pairs fly out from their target. They were measuring the angle between them, and most of the time, everything looked exactly like the textbook said it should. But not always. They saw a bunch more pairs than expected at one very specific angle.
So, this is the number you need to remember, around 17 megaelectron volts. This was the energy of that weird, unexpected bump they saw in their data. See, in particle physics, energy and mass are basically two sides of the same coin. So this wasn't just a random blip. It was a huge clue. It suggested that maybe the nucleus wasn't just a K anomaly. Maybe it was creating a new, unknown particle with a mass of about 17 MeV.
And that leads us right to the prime suspect in our mystery. Theorists jumped on this and proposed that the signal was being caused by an entirely new particle, a boson, which they provisionally named X17 after its approximate mass. And this wasn't just another particle to add to the list. Its existence would have, well, profound implications.
Think about it. If X17 is a real thing, it means the standard model, our entire rulebook for how the universe works at a fundamental level, the most successful scientific theory in human history, is incomplete. The X17 particle would have to be the carrier of a fifth fundamental force. That would be a revolution in physics.
Okay, so just as the excitement was really starting to build, our scientific detective story takes a massive plot twist. Another group of scientists using a completely different experiment went looking for the exact same clue in the exact same place, and what they found, well, it complicated things a lot.
And this is where things get really interesting. You've got this direct conflict. In one corner, you have the Atom K experiment, which repeatedly saw a significant signal in these beryllium-8 decays, and in the other corner, you have the MEG-I experiment in Switzerland, which looked at the very same decay and reported, well, nothing. No significant signal above what they'd expect from just random noise. And of course, this didn't go unnoticed. The physics community was all over it, with people online asking the exact question you're probably thinking right now. This is science in action, right? A result isn't really real until someone else can see it too. And here, the very first major check came up empty.
But wait, hold on, it's not quite case closed. In science, it's all about statistics and uncertainty. And when the theorists really crunched the numbers, they found that while the two results are definitely in tension with each other, they don't completely definitively rule each other out, yet. Statistically, they're compatible within what's called a 1.5 sigma range, which is a fancy way of saying the beryllium anomaly, while definitely on shaky ground, isn't completely dead.
So what do you do when you've got one experiment yelling yes, another one saying, maybe not, and these other positive signals from different elements just sitting there? You go back to the drawing board, right? Theorists started to ask if there's any kind of model, any kind of new particle that could possibly fit all of these seemingly contradictory clues.
And that brings us to this really fascinating paper that just came out. The authors basically took all the data, the positive signals from Atom Key and the null result from Mega 2, and threw it all into a pot to see if anything at all, could still make sense of it.
They were trying to answer this one key question. Is it possible for a particle to exist that is responsible for those signals they saw in helium and carbon, but somehow would have stayed hidden from the beryllium experiment that Meg 2e ran? Could the X17 particle still be out there, just playing hide and seek? And this table here, it lays out their findings perfectly. They looked at different flavors of what this X17 particle could be. One idea, a spin 2 boson, got pretty much ruled out by data from older experiments. But another possibility, a CP-even scalar particle, was surprisingly still on the table. And here's the crazy part. This type of particle actually can't explain the original beryllium anomaly. Now that sounds like a huge problem, but it might just be the key.
Okay, let me break that down, because it's a little counterintuitive. If we just assume for a second that the new Meg 2 result is correct, and there's nothing weird going on with that specific beryllium decay, a scalar particle actually fits perfectly. Why? Because the rules of quantum mechanics literally forbid a scalar particle from being created in that beryllium transition. So it could still be causing the helium and carbon signals while neatly sidestepping the one conflicting result. It's a very clever loophole.
So, where does that leave us? Well, the jury is still very, very much out. While that theoretical loophole is pretty neat, the wider scientific community remains deeply skeptical, and for some pretty good reasons.
And to get a real sense of that skepticism, just listen to this comment from a physicist who has actually published work on this very topic. They said that to make a model that fits all the data and dodges all the other experimental constraints, you need what they call a preposterous setup. It might be theoretically possible, but it requires a lot of things to be just so. And the concerns run even deeper than that. Some physicists point to inconsistencies within the Atom Key group's own data over the years. Others, a bit more bluntly, note that the group has a history of publishing some pretty dramatic but unconfirmed results. And maybe the biggest red flag of all, after nearly a decade, no other team, totally independent of the original group, has managed to see the same thing.
And yet, despite all that very healthy skepticism, the story's not over. And honestly, this is what's so cool about science. The possibility, however remote, of a discovery this enormous means that other experiments are being planned and are running right now to hunt for X17. The community is taking the anomaly seriously enough to spend real time and real money to either prove it's real or finally put it to rest.
Which leaves us right back where we started with our big question. Is this strange series of signals from the Atom Key Lab a glimpse of a revolutionary discovery? The very first crack in the standard model? Or is it all just a ghost in the machine, a subtle experimental error, or a statistical fluke that has led everyone on a fascinating but ultimately fruitless chase? For now, we'll just have to wait for the data to come in.